In this presentation, I will talk about LAMOST observations that have been done in the Kepler field, and it's a result of a large consortium, of which I list the main important ones here. And special thanks to Jianing Fu, who is here in the room, who is the driving force from the Chinese side. So you all know Kepler. It has been launched in 2009 and has provided about 4 years of continuous monitoring of one stellar field for more than 100,000 stars, either in short cadence or long cadence, and it provides broadband photometry with an accuracy of a few ppm. And the main scientific goals of this mission are to discover Earth-sized planets by using the transit method, and to characterize the planet hosting stars by means of asteroseismic methods. But it also gives us the opportunity to do astroseismic investigations of stars covering the whole HR diagram, which has been done in the KASC. So as you know, asteroseismology is a science in which we use stellar oscillations to study the stars. We want to probe the internal structure to derive accurate stellar parameters, have direct tests to the modeling of complex dynamical processes, and in the end, we want to improve our knowledge of stellar evolution. So what do we need for this type of study? We need precise pulsation frequencies, and we also need to know which modes are responsible for them. So these frequencies are directly provided by the Kepler light curves, and to do the mode identification, we can either use, we can combine it with ground-based follow-up observations, but that is basically only possible for the brightest objects. And, And if you see multiplets or regular spacings, that can also help you for the mode identification. But we should also not forget that to obtain the best results, we should also have strong constraints on the atmospheric parameters, as was also mentioned in the talk by Thomas, to distinguish between different solutions that can explain the observations. And in this plot here on top, I show you a recent calibration of the effective temperatures as a function of the spectral type. And the dots here are actually the values that have been obtained with KIC parameters. And as you can see, basically for the hot stars, there seems to be a discrepancy. So and that is where I think LAMOST could help to determine more accurate parameters. So LAMOST is a new telescope that is located in the Xinglong observatory in China here. So here is a picture. Here, this telescope here is a 2.1 meter telescope, which also can make high resolution spectroscopy. But LAMOST is actually these two buildings here. It's a 4-meter telescope that is capable of doing low resolution spectroscopy with a resolution of about 1,800 stars for many targets at the same time. So in the LAMOST-Kepler project, what do we want to do? We selected fields to cover the whole Kepler field of view, to characterize these targets in a homogeneous way, so to determine the stellar parameters, the spectral type, and to search for peculiarities. This is done with low resolution spectroscopy, so that also gives us some velocity information, and we can also get, in some cases, an idea of the rotation rates. And we chose this facility because it's the only instrument that we have now that is capable of observing thousands of spectra in an efficient way. And because the brightest targets can also be observed with other smaller telescopes elsewhere, in this project we are focusing on the fainter targets. So we made a large list, a target list, which is prioritized, and what type of targets do we want to observe? First of all, we need some standard targets to be able to do calibrations. This project originates from within the KASC, so we gave the highest priority to KASC targets, and in the beginning of our project, these were about 7,000. We added another 150,000 stars that were interesting for the planet search group, and on top of that, we added also other stars from the KIC catalogue, which doesn't have specific scientific interest to us, but, well, we can determine the parameters anyway. And to be able to make sure that most of the fibers are really filled, we also needed to add other field stars, which are not necessarily in the KIC catalogue. We also made a we also prioritized the targets according to brightness. So when LAMOST is doing an observation, it can only handle a brightness interval of about 5. So we made a distinction between bright targets and faint targets. So the bright targets are those between 9 and 14, and the fainter are fainter, of course. And even within these groups, we also made another prioritization. So for the bright targets, we mainly focus on the faint ones to avoid saturation effects. And for the faint targets, it's the other way around. We focus on the brighter targets to be able to, that we can obtain enough flux. And for those stars coming from the catalogue, we gave the highest priority to those for which no kick parameters are available. And for the rest, we prioritize from high to low effective temperature because the high temperatures are the less accurate ones. So in this plot here is a figure that shows the positions of the fibers. So in total, there are 4,000 fibers that cover a circular field of 5 degrees. And that is subdivided in 16 spectrographs with 200 fibers each. So this is one of these little circles here. So the fiber is actually mounted here at the end of this second shaft. So these shafts can move in different directions. So by combining this movement, you can actually reach every point within this circle. These circular regions also overlap. So when you are pointing the fibers to the stars, you first allocate regions that can only be reached by 1 fiber, and in the next phase, those with 2 fibers and 3 fibers. And also each spectrograph, you should make sure that there are at least 5 fibers that are filled with standard stars, and at least 20 fibers with no object at all to be able to have a sky spectrum. So for this proposal, we selected 14 fields to cover the Kepler field of view. These are depicted here with these circles here. And we try to optimize the position of these fields of view to optimize the number of observable KASC targets. And for one of these, well, for each circle, we need to make sure that in the central hole is a bright star with a magnitude below 8, and in the off-center holes they should contain a target with magnitude below 17, but that's normally not a problem. So the observation started in 2011. In that year, there were only observations in 2 nights, and 1 field was observed. In 2012, 3 more fields were observed on 3 nights. In 2013, 6 more fields were observed in 11 nights. So in the first 3 years, we obtained more than 60,000 spectra. And I should also mention that while these observations are still ongoing, so far in 2014, 3 fields have been observed, 1 new one, and two ones have been reobserved during 3 nights. And after the closure of LAMOST for the monsoon season, the observations will continue, so we have high hopes that the remaining fields without observations will be observed this year. So in the remaining of the talk, I will focus on the analysis that we have done so far for the 2011 and 2012 spectra. So here I give you a few examples of LAMOST spectra. So on top are the full spectra. Here below is the blue region containing the calcium H and K lines. This is the H alpha region, and this is the region in the near infrared. So on the left, I show you a B-type star, in the middle a G-type star, and on the right, an M-type star. And as you can see, they clearly look different, so that is why we can use them to do the spectral classification and to determine the parameters. So this is a small statistical overview of these observations of 2011 and 2012. I give you a distribution of the magnitude, and for those for which kick parameters are available, the metallicity, effective temperature, and log G. But I just wanted to show here in its HR diagram, by using this data alone, we can already check the accuracy of the kick parameters in the majority of the HR diagram. So the members of the Chinese team, as we call them, they use the code ULySS for for determining the parameters. This is a chi-square minimization of a fit of a parametric model to the observed spectrum. So, and this model is actually a linear combination of nonlinear components that are convolved with a line of sight velocity distribution. And this as a whole is multiplied by a polynomial function. And this is done in pixel space. So in our case, these linear components are actually stellar models that depend on the stellar parameters. And this multiplication by polynomial fit is done to observe effects of imprecise flux calibration and of galactic extinction. So this code has been adopted to the LAMOST observations, so for a resolution of 1,800. And it can determine effective temperature, log G, metallicity, and radial velocity. And the first three can be compared with the Geek-10 parameters, which are based on Sloan photometry. So this is done here for the effective temperature. And on the figure, the 5 nights that I consider here are given another color. And as you can see, the correspondence is quite okay, and the mean difference is about 170 Kelvin, and the maximum difference for a hot star is found to be 6,900, which is already quite big. This is the situation for log G. It looks a little bit less nice, and we found here a mean difference of 0.35 dex and a maximum difference of 5 dex, which is huge. And this is the situation for the metallicity, and as you also might have seen in the distribution, both the Geek mean value and the ULySS mean value are negative, so that gives you the impression that there are many metal-poor stars. But the bulk of the observations are situated here, which are compatible with solar metallicity. I should also mention that Subodong et al. Used also LAMOST observations with the more recent version of the reductions. And they found an expression to convert from LAMOST metallicity to Geek metallicity with a non-zero, with an inclination and a non-zero offset. And the scatter around this formula is about 0.26 dex. And they also showed that LAMOST metallicities are in good agreement to those that were determined from high resolution spectroscopy with the spectroscopy made easy method. So within the European team, as we call them, that is centered around the group of Antonio Frasca in Catania, we used the ROTFIT code that has also been adapted to LAMOST spectra. So first what we did was a semi-automatic normalization of the spectra with IRAF. In this method, a library of more than 1,000 spectra is used for stars with known stellar parameters, but they had to be degraded to match the resolution of LAMOST. And then the comparison is actually done within slices of wavelength, and the final parameters are determined or derived as a weighted mean of the parameters of the 10 best templates for each slide. These are an example of the results. Here I show you a part in the blue and in the red. So I hope you can see it. So the black dots are the LAMOST spectra. The red line is actually the best template fit. And here in blue are the residuals. And as you can see, these residuals are quite small. So this is an example of an A-type star. Here is an F-type star. You can still see that the residuals are small. And a cool G-type star. And as you can see, the even small absorption lines are fitted quite well, let's say. We try to validate our results by comparing our parameters with those that can be found in literature based on high resolution spectroscopy. So this is the situation for effective temperature, which looks rather nice. So here I show you our results, and on top are the literature results, and here are the differences. So the mean difference is about 0, and you can see here that the error basically is about 4% between these two. This is a situation for gravity, and you have the impression that there are two clouds here, which is a reflection of the use of our library, basically, because it contains main sequence stars and evolved stars, and that is reflected here. And the sigma in this case is about 0.30 dex. For the metallicity, again, the majority seems to be compatible with solar metallicity, but you also find some evidence for metal poor stars. And you see here some kind of trend, which is a reflection of the fact that metallicity and effective temperature are correlated in the determination. And here we find a sigma of about 0.25. We also try to determine the radial velocity, and we did this by making a cross correlation between the observed spectrum and the best spectrum, the best template from a list of 20 spectra with different spectral parameters from this library that we use. And the best is considered as the one with which gives the highest cross correlation peak. And as you can see from the figure and from the comparison here below, there seems to be a mean difference of about 8 kilometers per second, and the sigma is about 13 kilometers per second. But this 13 kilometers per second is actually also the precision that the LAMOST people give for the wavelength calibration, so that is compatible. We also try to get some information of V sin I, but that doesn't seem to be very easy, which is normal because we are dealing with low resolution spectra. As you can see in this box here, for slowly rotating stars, you basically can say nothing, but because the difference between what is known from literature is so huge. But only for stars with a V sin I above 150, we can say something. I will skip this because I'm running out of time. In America, they're also trying to use a new program to do spectral classification in the same way as is done by the humans. So what I wanted to show with this presentation is that this LAMOST-Kepler project is actually an ambitious observational project that can provide rather accurate stellar parameters derived from low resolution spectra in an efficient way, because we have 4,000 fibers, and also for fainter stars than for most ground-based facilities. The project is not finished yet. Not all requested fields are observed, but we have hopes that it will be done by the end of this season. And also not all observed LAMOST spectra are analyzed yet, so we still have some work to do. If you are interested to get LAMOST spectra that is already available, you can send an email to me and I can send it to you. And I want to finish with this slide to announce the first LAMOST-Kepler workshop that is being held in Beijing next month. And you're still welcome, because we can still welcome a few people. That's all. Thank you.
I think Daniel was first on that one.
I have a comment and a question. So the comment is about the planet search targets with Kepler. So it might not be a well-known fact that Kepler, the planet search pipeline is run on all stars, and so not just the ones that were selected to find planets. So all the KASC stars and everything that's been observed is also searched for planets. Yeah, so I would encourage to include everything and not just.
But in the beginning of the project, I contacted Natalie Batala to ask if she has a list of stars that were interesting for her, for our group, and that was the list that I obtained. Okay. So that's why they came in the project. Right.
Okay. The question is, have you done? So I've seen the comparisons of the log-J's from LAMOST. Was that was for solar type stars as well, and or just for hot stars? And related to that, have you done any checks with asteroseismic log-G's? Or just from high resolution spectra?
Well, we basically concentrated now on a high resolution spectroscopy to do a rather homogeneous comparison. But this includes everything that we could find. So it includes all, targets that were in common between our sample and what we could find in literature. I'm not claiming that it's complete, but that's what we find so far.
Yep.
Yeah, two questions. One, do you happen to know offhand if any R-Lyra stars or SX Venisa stars were observed? And secondly, how many spectra do you have of your individual objects? How many repeat observations?
Well, I can start with the second question. Well, as you can see here, well, some of these fields have been observed more than once already. Either because, well, the earliest observations were in the testing phase and the commissioning phase, so there were still some problems. So, for example, Yeah, so for example, these two fields here were re-observed in 2014, so there will be certainly stars with more than one observation. And you can also see that there are fields with, well, they slightly overlap, so there are stars with more than one observation. But for your question about RLI stars and others, I can't say it like that. We didn't make any distinction between the type of stars in the construction of our target list. So there's a possibility. So if you want to, if you give me the Kik numbers of your stars, I can check if they were observed or not.
You seem to try to calibrate your results with the Kik catalogue, but the Kik catalogue was proven by numerous authors to be off in several parameters.
Can you repeat? Sorry?
You seem to be trying to calibrate your results with the Kik parameters.
No, at this moment we are just comparing them, and we see that there are differences. That's why we also compare with what is known from literature, from things we trust more. So actually the validation as for the European group is basically done by comparison with results from high resolution spectroscopy and not by comparing with Kik.
Okay, so we have a question here.
It was practically the same than the previous question. I was wondering on this coefficient of, when you had the metallicity conversion between the Kik and the LAMOST metallicities with a factor of 0.4 for the metallicities of LAMOST, which really shows, I think, that one of the catalogs is totally off against the other one.
But in this paper, so they do show that there's a slope if you compare the Kik with their results. But as I say in the second point, they also compared their results with results that are based on high resolution spectroscopy, and they seem to be aligned. So that's why they conclude that the results with ULySS are more accurate than those obtained with Kik.
So the Kik metallicities are really to handle with great
Yes,
reservations.
so they should be handled with care, let's say.
Thanks.
Last comment there.
Okay, I just would like to add that the more than 60,000 spectra were made for more than 32,000 stars. Is that clear? So almost half of them, a lot of them have been observed twice.
Yeah.
For the stars. Okay.
Okay, so let's thank the speaker again.